name is Nathan Northrock, and my paper discusses the use of electronic ring laser gyroscopes. Some background on this topic: gyroscopes are critical components to aircraft that are used to calculate things such as airspeed, angle of attack. These are critical parameters that the aircraft needs in order to execute all the operations that it does. Electronic gyroscopes were developed as a replacement for mechanical ones. Before electronic technology, analog systems were used to calculate these parameters for the aircraft to perform the way that it does. The research paper written by shows some of the parameters and aspects of electronic gyroscopes that are better than mechanical ones, such as more rapid response, higher precision, higher reliability. Because of these, electronic gyroscopes are widely used today, and much more than mechanical gyroscopes are. For this paper, I also developed 3 hypotheses, and we will discuss each one in turn. First hypothesis is the stagnant effect of splitting a beam into 2 halves provides more precision than mechanical gyroscopes. The stagnant effect is if scientific principle when you split a beam into 2 around a container ring, and then when that ring is rotated at a particular speed, there becomes a phase difference in the 2 lasers when they join back together. Now, this phase difference can be used to detect the amount of rotation, velocity, all sorts of different parameters to be used into helping an aircraft fly. So this is the basic principle of how electronic gyroscopes work. They rely on the stagnant effect to perform. We also here provides an explanation as to why the stagnant effect is so critical. All of these parameters rely on it to perform, and you can get very precise calculations using these parameters. There's a whole host of equations that by using these you can determine down to minute details of what the aircraft has performed just through electronics. This is a representation of what a ring laser gyroscope would look like, and you can see here the stagnant effect of the beam splitting, going around the ring here, and then ending up with the detector at the end, and that detector will then be used to calculate the phase difference so that the other parameters can be calculated as well. My second hypothesis was that constant monitor and adjustment in the random motion of the dither frequency is better at preventing synchronized frequency and the creation of standing waves. The most common fault in these electronic ring laser gyroscopes is lock-in. Now, this lock-in occurs when the 2 split beams lock in together and create a standing wave. Now, that standing wave becomes unmovable. No amount of rotation will change that standing wave. This creates no phase difference change, and therefore any physical changes in the aircraft will not be shown through the electronics in the gyroscope. Now, the current techniques to eliminate this lock-in standing wave is called dithering. Dithering is a mechanical vibration of the ring laser gyroscope itself that causes small vibrations to where the lasers can't match their phases, so there will be no standing waves created. This is still a pretty frequent occurrence in monitoring modern electronics. But my research through the John here, in this quote, that if you can constantly monitor what that dither frequency is, and the dither frequency of the gyroscope itself, you can better move the lock-in frequency out of that area, and this provides better relationship, better prevention of a static wave. This requires more electronics to be added, of course. You will need more of a constant monitoring system, and this increases the complexity of modern aircraft. But with the way technology is moving, you can reduce the amount of circuitry required, the amount of systems needed to have this constant monitoring, but if you use it, you can keep things out of that area. My third hypothesis was that material qualities of glass ceramics increase the overall quality of the internal laser. So the ring laser gyroscope is within a almost triangular glass ceramic material, and the laser is internal to that laser within a cavity that is filled with a gas. I've read a lot of papers on it, and there's best I saw was Fouchaux's quote here, that the best gas to have internal to that to create the best quality laser is a 10-to-1 mixture of helium and neon. He calls out two specific isotopes of neon that are necessary to provide the best quality laser. If you have a poor quality laser, you can't discern that phase difference as well, and that leads to irregularities in the measurements and the calculations, and you don't always get as precise of a value as you could. This is a better diagram of the one before, of the buildup of a ring laser gyroscope. You can see the triangle feature. There are mirrors in all those corners there, with the detector down at the bottom right, and that internal cavity is filled with this gas, and that's what produces the best quality laser. In conclusion, with hypotheses, the side-nectar effect of electronic gyroscopes is much more reliable than mechanical gyroscopes. Mechanical gyroscopes have largely been phased out of modern aircraft and replaced with these more advanced electronic ring laser gyroscopes. Constantly monitoring and adjusting dither frequency using piezoelectric sensors provides the optimal method for preventing critical lock-in fault error. This monitoring is crucial to keeping the gyroscope dither away from the dither frequency of that lock-in. Glass ceramic materials using surface of 0 to provide the best physical characteristics. These ceramics are the best to use for lasers and provide the best laser quality over the course of the ring laser gyroscope. The ideal medium inside the laser cavity is a 10-to-1 mixture of helium and neon. The two isotopes of neon, called for, provide the best quality, and this helps to deliver more accurate and precise readings, and therefore a better, more reliable system for the aircraft to use. These are my references. Thank you for listening.